Pichierri?
Is this Pichierri?
Okay, I pronounce it well. Good. So Gabriele Pichierri, who will speak about the stability of resonant pairs of super Earths.
I'll give you a sign. Okay, do you hear me well? Yes. So I will present this work with Alessandro Morbidelli of Elanqida that we've done on the stability of resonant pairs of super Earths. So to give some context, super Earths are these planets with a mass about 1 to 20 Earth masses and period about less than 100 days, and they're estimated to orbit up to 50% of Sun-like stars, so they're really common. Multi-planetary systems are not rare, and so they give some constraints to formation models. And one of these models is that of migration in protoplanetary disk, which predicts a capture in a mean motion resonance. So we would have all these planets locked into compact chains of mean motion resonances. However, the observations do not show this, and actually most of the systems are not in resonance. And in fact, I can cite this work here where they show that about 50% of these systems would become unstable, and they argued that the Kepler data suggested that actually 95% of these resonant chains would go unstable. So the idea is that the origin of the instability is not fully understood, and so we would like to apply celestial mechanics to understand this. So this is just a plot that we already saw about the period ratio distribution of these systems. Here I just used the two-planetary system because we're just dealing with 2 planets here, and here the distribution of all the number of planets in the system. So the aim of this study is to obtain an analytical model for first-order mean-motion resonance with 2 planets of equal mass, to follow the evolution of numerical simulations that we run, and to understand the mechanisms that lead to the instability of these systems. So this is our model, is the planar 3-body problem Hamiltonian. So we have a star and 2 planets of equal mass, which are orbiting on the same plane. So we write Delaunay action angle variables, and we write the Hamiltonians as usual. At this point, we assume a first-order mean motion resonance. So the mean motions satisfy the resonance relationship. And we take the Hamiltonian and we average it around, over the fast motion. So we average over, for example, lambda 1 from 0 to 2 k pi to obtain the full periodicity of the Hamiltonian. And in fact, we just need to do this for the perturbation part. And because of the D'Alembert rules, only angles like this will survive. So we will have a resonant angle, this guy, and then we will have the difference of the perihelia of the 2 planets. And so it's convenient to introduce resonant variables. So we have here the resonant angle, which will librate, and then the delta of RP, which is gamma 1 minus gamma 2, which will librate, and then we have the 2 actions conjugated, and then we have one angle which will not appear in the average Hamiltonian, and so we will have a constant of motion, and then we have this angle which doesn't appear in the Hamiltonian, so we have another constant of motion. And quickly, what we've done, we obtain a 2 degree of freedom Hamiltonian, which depends on these 2 actions, big C1, big C2, and the 2 angles, which are the resonant angle and the difference of the perihelia. And it depends parametrically on K and this omega, which are constants of motion. So quickly, K yields the location of exact Keplerian resonance because we will see, and it's well known, that for low eccentricities, the ratio of the semimetric axis actually drifts away from exact Keplerian commensurability. So this means that when we see the peaks in the diagram that I showed before with the ratio of the 2 period ratios, the fact that they actually pile up to the right of the exact Keplerian resonance doesn't mean that these systems are not in resonance. They may be in resonance. So the K tells us from the observed A1 and A2 where the location of exact Keplerian resonance is, and we can do it pretty easily. And then again, so I have 2 constants of motion. Of course, they have to be linked to the total angular momentum of the system. So this relationship here. So now what we do is to obtain our model of resonance. We fix a value of K, so we fix the location of the resonance. And then for different values of angular momentum, we find a double equilibrium point in the variables that we have for the Hamiltonian. So in our simulations, we see the resonant angle librate around 0 and the delta of RP to librate about pi. And so we maximize H bar over the 2 actions that we have. Okay? And so with this, we obtain plots that probably you have seen already. So we have, for example, for the 3:2 mean motion resonance, here we have the ratio of the semi-major axis. This is the exact Euclidean location. This is the eccentricity E2, and this is each point on this curve is for one level, one value of angular momentum, one equilibrium point for the Hamiltonian that we have. So here is, for example, for a mass of 10 to the minus 5, the mass of the star. This is for the 4:3 mean motion resonance. The next slide is for the 2:1 mean motion resonance. And I just show this because in blue I have again our equilibrium curve that we calculated with A2 over A1 and A2. And this dashed line is the equilibrium curve that we would get if we use the first order expansion in the eccentricity. So this means that with a first order expansion in the eccentricity, we don't get the geometry of the resonance right. This would be a second order expansion, which kind of gets the geometry right, but in fact with this the Hamiltonian that we considered with this curve, we obtain exact not only not only the geometry is right, but also quantitatively the levels are right. So the equilibrium that we find are exactly the equilibrium of the system. So now we have our model, and we want to do we want to put these systems in resonance. We do this using a slow type 1 migration in a disk with a disk edge at 0.1 AU, and we assume planar, initially circular planets, equally massive planets. So the effect of the disk is to damp E. That's why we consider initially circular planets, and this would cause inward migration. And to assure that we have capture and resonance, we smoothly reverse the sign of migration at the disk edge with a disk trap, and this results in convergent migration. And what happens, as we already saw in this conference many times, is that we start from A2 over A1 and E about here, and we follow, if the dynamics is low enough, we can apply a adiabatic approach, and we can say that we follow the equilibrium curve up, 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 okay? And we can calculate when the equilibrium is obtained by balancing the eccentricity damping of the disk and the excitation due to this resonant dynamics. And so we obtain an equilibrium configuration, and then finally we slowly deplete the disk, and we reach a final resonant stable configuration. And we can do this numerically, and we can obtain analytically the values that we observe. So this is just a few plots of this. So we have, for example, the 2:1 mean motion resonance. We see the two planets migrating in. The first planet stops here at about the disk edge, and then the second one gets trapped, gets captured in resonance, and the two eccentricities go up. This is for the 4:3 mean motion resonance. And the next slide is for the 3:2 with different masses. So here I have A1, we have E1, A2, and E2. So for different values of the masses of the planets, again, these are equally massive planets. And we see that the eccentricities that I obtained are independent of the mass, and this is understood analytically. And of course, instead, the value of the semi-major axis will be different because the equilibrium curves are different. And so this means that for one fixed eccentricity, the equilibrium value for A1, for example, will be different. So the ratio A2 over A1 will be bigger. Okay, and we will see this in the next slide, actually. So so we do an exercise. We fix the planetary mass. We do the migration game. We obtain the configuration, and then we deplete the disk. So we obtain basically a final angular momentum, L. And then, so what we've done basically is we follow the curve here, this curve, and then we stop here, we deplete the disk, and so we are here on the equilibrium point. Then what we do is we adiabatically slowly increase the mass of the planets. Okay? So we can, numerically, this is what happens on an A2 over A1 E2 plane. We have all these dots. This is a numerical simulation. Analytically, I can say that the system will evolve following the lines of constant specific angular momentum, so this guy here. And so what happens analytically, how do I follow the system, is I just follow the different equilibrium curves for different masses, imposing that I follow the line of constant specific angular momentum. And so analytically, I calculate this line, which fits very well the simulations. That's all I have to say about this. So this is just to show, here I have the mass of the planet on the x-axis, and here I have A1, A2, E1, and E2, and so these are numerical simulations in blue, and the black line is the analytical calculations that I do, and I can see that I follow very well the dynamics. This is again for the 3-to-2 mean motion resonance. And what I observe is that at some point in the mass, I have immediate instability. There is a critical mass above which the system goes unstable. Okay. So this is just to prove this. So this is a figure for a mass about smaller than the critical mass, just below the value that I found of the critical mass. And here I plot the resonant angles. Okay. So these C1, and this is the other resonant angle, the one without the gamma 1, but with the without the bar P1, but with the bar P2, basically. And I see that they're librating around 0 and pi. So these systems are in resonance, and they stay in resonance for long integration times. The semi-major axes are oscillating, but these are fast oscillations due to the lambda 2 minus lambda 1 angle. So these are angles that I actually averaged out. So I show this here, that the period of oscillation of A1, for example, is linked to the period of oscillation of lambda 2 minus lambda 1. And the same is for the resonant angles. So they're fastly oscillating due to the lambda 2 minus lambda 1 angle. And instead, for a mass just about after the critical mass, I see that the system goes almost immediately unstable. Okay, so these are the resonant angles, and this is the semi-major axis of the first planet. So again, so what we see is that in our simulation, when we slowly increase the mass, that we can follow analytically after a certain critical. So my analytical model would go on forever, but actually I found a critical mass after which the system goes unstable right away. For smaller critical masses, the system becomes stable and the oscillations are short periodic due to the synotic angle lambda 2 minus lambda 1. And for a bigger mass, the system goes unstable right away. So why does this happen? So the reason we note there's a commensurability between the libration frequency around the equilibrium point. Okay, so the resonant angle is librating, and another characteristic frequency of the system, that of the angle lambda 2 minus lambda 1. So in this case, this simulation is 2 to 3. So it's a small first order secondary resonance between these angles. Okay. So of course these angles I was not considering in my model because I averaged out. So we plot what we do, because at the beginning I said that the eccentricity that I would get after a simulation with migration does not depend on the mass. Okay. But the semi-major axis does. So what I should do, because then that would mean that I would follow. When I do a simulation with a different mass, I would get to the same eccentricity but on a different curve, and then I would follow another line of specific angular momentum. So it would be wise to have a plot of all possible libration frequencies around these points for all the masses, not just, of course, this particular value, this particular equilibrium following the dynamics. So this is what we do, if we can get there fast enough. Okay. It was right there. Okay, so here I plot the mass of the planets, okay? And here, for example, the eccentricity, E2. And these are lines, these are a contour map for the libration frequency around the equilibrium point, okay? And so these lines go like this, and then they come back. And these are lines in which, so this level curve would be a 1 corresponding to a 1 to 2 resonance with the angle lambda 2 minus lambda 1. And this would be a 2 to 3 resonance with that angle, and this would be a 3 to 4 resonance with that angle. Okay, this is the simulation. Actually, it's the analytical calculation of the evolution of E2 with respect to the mass, the one that I showed before, comparing it to a simulation and seeing.
Sorry, what is the primary resonance here?
Comment?
Well, which
one? It's the 3 to 2. Yeah. Yeah, I haven't written. And so we see that the instability appears exactly there where I have a secondary resonance, the 2 to 3 resonance with this angle here. Okay? And so we deduce that the reason of the instability is this secondary resonance, low order secondary resonance with another characteristic frequency of the system, which of course my analytical model was not taking into account. Another thing I can say is that these curves curve like this. So one thing that one could say is because the eccentricity, the equilibrium eccentricity is proportional to the aspect ratio squared of the disk. Okay. So in final stages of the disk, the aspect ratio would go down, so E2 would go down, and so basically, of course, the planet would have a fixed mass, so I might follow a curve going like this, and so I might encounter a secondary resonance, and so I might go unstable. But this has to be checked. Well, it has to be checked. Okay, so then finally, I don't know how I'm doing on time. I'm fine. So we check so my criterion for stability would be I follow the dynamics starting from here until I encounter some secondary resonance. So I have a region of stability which would be about here, okay, and then after I have an instability. And so we compare this with another criterion for stability or instability of closing planets, that of the mutual Here radius. So the criterion goes that if the distance becomes smaller than a critical distance, which is given 2 square root of 3, the mutual Here radius of the two planets given here. If this happens, then I would have instability. So of course, if the two orbits are anti-aligned, the closest encounter I could get for any orbital configuration possible would be when the second planet, the outer planet, is on a pericenter, perihelion, and the inner planet is at aphelion. Okay, so this would be the critical distance that I would have. But actually, the resonant condition keeps the planet from obtaining this configuration because this angle is about 0. So this does not allow this configuration to appear. And so we expected that my criterion would predict more stability than the Hill's criteria stability with this distance considered. And then another close encounter would be when the outer planet is at aphelion and the inner planet is at perihelion. Okay, and so this would be given by this distance here. Okay, and so we compare this criteria with our criteria. So this would be the first one. Of course, it's a really small region of stability. So this would predict that the system goes unstable here, which it doesn't. And the second one would has stability here, and then instability starting from here. But in fact, it doesn't happen. In fact, my system goes on and does not become unstable even after this critical distance is attained. And so conclusions. So the takeaway, we have a complete understanding of the process of capturing to resonance and the equilibrium values for the semi-major axis and eccentricity. We mapped the resonant equilibrium points for all values of planetary masses and angular momentum in agreement with numerical simulation. And we identified the mechanism which destabilizes the resonance, which again is a low-order secondary resonance between the libration period in the mean motion resonance and the circulation period of λ2 minus λ1. And then we mapped the stability limit on a frequency map, and in terms of the mass of the eccentricity of the second planet, for example, and we compare it with the Hill stability criteria. So future work might include studying specific system and apply this scheme for multiple planets, not just 2 planets. Well, thank you very much.